In 2022, NASA carried out the first full-scale asteroid deflection test in human history. The DART mission targeted a small asteroid moon called Dimorphos, which orbits a larger body named Didymos. The objective was to strike it directly with a high-speed spacecraft and measure how much its orbit changed. The collision happened exactly as planned. Dimorphos was hit, and its orbital period was reduced by over 30 minutes. But the story didn't end there. What followed was a series of events that exposed the true scale and violence of this kind of impact. It wasn't just a shift in trajectory, it was an explosion in space. Debris, dust, and massive boulders were hurled outward with force far beyond what had been modeled. The aftermath of the impact is now raising concerns about what this method might actually cause if used near Earth. Because what DART triggered was not a clean redirection. It was a chaotic release of energy, momentum, and destruction. When DART slammed into Dimorphos, it delivered a powerful kinetic punch. The spacecraft itself was small, but its velocity was extreme. Upon impact, the asteroid's surface fractured instantly. Cameras on board a trailing satellite, LICIA cube, captured what happened next. More than 100 large boulders were thrown from the surface. Some were more than 3 meters wide. The largest cluster traveled in a concentrated band, moving at speeds of up to 52 meters per second. These boulders were not drifting lazily into the void. They had momentum far beyond that of the spacecraft. In fact, the momentum contained in this single cluster was over 3 times that of DART, and their direction was not forward. The material was ejected almost sideways, at angles nearly perpendicular to the trajectory of the spacecraft. That ejection pattern created unexpected side effects, not just around the impact site, but in the motion of the asteroid itself. Dimorphos didn't just absorb the hit, it reacted. The sudden ejection of mass caused the asteroid to recoil. It altered not just the speed of its orbit, but also the orientation of its entire path. According to the latest analysis, Dimorphos's orbital plane may have tilted by as much as 1 full degree. That kind of change matters, especially when the system is used as a model for future asteroid deflection scenarios. But there's more. The impact didn't just push, it twisted. The sudden directional blast of boulder clusters likely shifted Dimorphos into a state of non-principal axis rotation. That means it no longer spins cleanly. It wobbles. It may now be rotating in multiple directions at once, in a motion that could persist for years. The Hera spacecraft from the European Space Agency is scheduled to arrive in 2026 to measure what's changed. But until then, we won't know how long the instability will last or how deep the structural effects truly are. The biggest concern isn't what happened to Dimorphos. It's what was left behind. Over 100 massive boulders are now drifting freely in space. Many are outside the main debris cone. Some are still within the Didymos system, but others are moving outward on new paths. We do not have a system to track objects like these. They are too small, too dark, and too fast to be followed from Earth. And yet they carry enormous momentum. Each one is now an uncontrolled projectile in open space. If this same method were used to deflect an object closer to Earth, these secondary fragments could become a new kind of threat. Not from the original asteroid, but from the debris field left behind. Satellite constellations, space stations, even Earth's atmosphere could be impacted depending on the angle, speed, and survival of these fragments. This isn't hypothetical. It already happened. We just haven't seen the long-term consequences yet. NASA's DART test was a technical success. It proved we can change the path of an asteroid using kinetic force. But the details emerging from the aftermath show that this method is not controlled. It's not clean. It creates new problems. Dimorphos is now rotating off-axis. Its orbit has tilted, its surface is scarred, and surrounding it is a spreading cloud of high-speed debris, some of which may still be accelerating. This is what happens when raw kinetic force is applied to a celestial body. And here's the reality. This is the only method we've tested, the only real-world demonstration of asteroid deflection. There is no second plan, no controlled capture system, no mitigation for the fallout. The Hera mission will arrive in 2026 to scan what remains. Until then, what DART created will continue to drift, And when the time comes to stop a real threat to Earth, we'll have to decide whether to risk scattering the sky to stop a single rock.